Welcome back to the channel. If you want to understand the hidden mechanics running our digital world, hit subscribe. When an enterprise AI assistant fails to secure a financial system, it's often because the agent lost the memory of its own security protocols. This gauge tracks production agents in enterprise workflows, where 94% currently fail basic safety checks. These failures persist because systems are evaluated on their ability to complete tasks, rather than the security of the steps they take to get there. This emphasis on functional output creates a gap between the efficiency of the AI and the safety of the underlying network. Consider a bank's AI tasked with processing a continuous stream of credit approvals. This timeline illustrates context decay. At the 10th interaction, the system drops the specific regulatory parameters it was required to verify. Fixed-size context windows attempt to solve this by forcing the system to manually rewrite its prompt every 10 interactions. These constant resets are a primary reason agents miss critical compliance steps during extended operations. Prioritizing immediate output over long-term context retention leaves the system unable to maintain consistent security standards. Adapting memory to retain specific critical nodes allows the system to operate with intentional recall. While memory retention is a technical hurdle, a deeper vulnerability exists in how we evaluate agent security. This chart reveals that only 14.5% of context files in production agents explicitly outline security requirements. With the focus remaining on performance metrics like latency, 90% of these agents operate with undetected vulnerabilities. An agent may answer every user command perfectly while dropping the specific instructions needed to ensure data remains encrypted. Forcing accountability into the initial design ensures that safety is a foundational requirement rather than a post-launch addition. Redefining responsibility in AI means moving beyond the trade-off between operational speed and system safety. Financial firms employing dynamic memory have seen a 62% reduction in compliance risks. In healthcare environments, this same structural overhaul reduces patient error rates by 37%. Addressing these failures at the architectural level targets the cause of context loss rather than managing the errors after they occur. Scaling enterprise AI requires proactive memory and predictive security to prevent the loss of billions in the coming months. Engineering accountability into the default architecture is the next stage of AI development. We must determine who bears the responsibility when an autonomous agent forgets its operational constraints. Self-regulating architectures track their own security compliance, dynamically adjusting their memory limits based on assessed risk parameters before they cause harm. Systems designed to fail safely before causing harm represent a vital step toward technology that respects its users. The strength of an AI system is found in its ability to determine exactly what it should not remember. A March 2026 survey of the AI infrastructure community found that the performance gap between agents with memory and those without is often larger than the gap between different LLM backbones. Engineers often assume that stacking parameters and expanding context windows will solve complex reasoning bottlenecks, building massive models that eventually crack under their own weight. But ablation studies suggest that capability is driven by memory architecture, not just model size. This chart tracks the performance of the Voyager agent. Removing its procedural memory library causes the system to operate 15.3 times slower than the baseline. These benchmarks suggest that memory architecture functions as a primary computational engine, directly dictating an autonomous agent's performance. To evaluate these systems, we must first define the three distinct cognitive functions a memory architecture must perform. Episodic memory is the time-stamped timeline of specific interactions, enabling single-shot learning. Semantic memory stores abstracted facts and entity relationships as a stable knowledge base. Procedural memory holds learned workflows, allowing an agent to improve its operations over time. Most production deployments in 2026 still rely on basic semantic RAG for their knowledge retrieval. True long-term autonomy requires an architecture that can unify and manage all three of these memory types at once. For volatile enterprise environments, Zepp uses its Graffiti engine to handle data that changes frequently, stealing data points and consolidates them into an organized central core. This framework sheds the noise of past interactions while keeping essential parameter nodes active across an unbroken timeline. Across 10,000 real-world interactions, this architecture reduces context decay by 62%. A banking agent can now process 30 complex approvals in a single chain without losing track of the regulatory requirements. Adapting memory to retain specific critical nodes allows the system to operate with intentional recall. Standard knowledge graphs fail here, overwriting old nodes and losing historical context. Graffiti is temporally aware. It preserves previous states and connects them across a timeline. The graph organizes into 3 tiers: episode interactions, semantic relationships, and community clusters. On the deep memory retrieval benchmark, ZEP achieved 94.8% accuracy, slightly ahead of MEMGPT's 93.4%. The long MEM-eval benchmark showed that this architecture reduced response latency by 90% while improving accuracy by 18.5 percentage points. In enterprise settings, these temporal graphs prevent the agent from hallucinating outdated facts by maintaining the history of data transitions. MEM0 takes a generalist approach. It currently leads 2026 benchmarks by routing queries across multiple specialized databases. This query router directs each request to the most appropriate backend: a vector store for similarity, a graph store for relational knowledge, or a key value store for fast lookups. This configuration scored 91.6 on the Locomo benchmark, a test for long-term memory. MEM0 achieves the score using only 6,956 tokens per query. A full context baseline costs approximately 26,000 tokens. But what if the retrieval pipeline itself is the bottleneck? LEDA treats memory as an operating system problem. The agent does not just receive data, it actively manages its own storage hierarchy. This hierarchy moves data from fast in-context memory to a recall store for recent history, and finally to an unlimited archive for long-term storage. Instead of using an external retrieval engine, the agent uses its own tool calling capabilities to move data between these tiers. In LEDA's own evaluations, agents using standard file system operations like grep and search reached 74.0% accuracy, outperforming MEM0's 68.5% on the same task. These results suggest that if a model is trained extensively on tool use, simple file system operations can perform as well as specialized database infrastructure. As we move into 2026, we are seeing a gap between benchmark success and production reality. Models that appeared nearly perfect in evaluation often fail in the field. While systems score 90% on the Locomo benchmark, their performance can plummet to 40% on the Memory Arena evaluation. Memory Arena requires the agent to use information from an early session to interpret data in a much later session, testing utility rather than simple recall. The latest research survey describes this as a deep gap between passive data recall and active, decision-relevant memory use. Recalling a fact is only useful if the agent's architecture allows it to weight that fact correctly during a live task. 6 open research problems currently stand between current prototypes and scalable enterprise deployment. Problem 1 is temporal abstraction scale. Retrieval performance drops by 25% when a system scales from 1 million to 10 million tokens of history. Problem 2 is cross-session identity resolution. We cannot yet reliably unify a user's memory across mobile, desktop, and API threads. Problem 3 is memory staleness. There is no automated mechanism for detecting when high-confidence memories from the past have become obsolete. Problem 4 is learning to forget. Deleting specific data from model weights to meet privacy regulations remains a significant technical hurdle. Problem 6 is evaluation methodology. The industry lacks a standard way to measure production utility as opposed to benchmark performance. The teams that solve these 6 vectors will define the infrastructure standards for the next generation of AI. For 2026 deployments, the most critical design pattern is aggressive write path filtering. You must rigorously filter the incoming data stream. Only perfectly uniform, relevant information should ever reach the agent's core memory. Every unfiltered piece of information added to a memory system acts as noise, eroding retrieval precision as the history grows. Investing in your memory architecture today offers massive returns that exceed the benefits of waiting for a larger model release. The next model will be expensive and outside your control. Memory architecture is an engineering decision you make today to determine how your agents actually perform. Thanks for watching. If you want more deep dives into the hidden systems shaping our technology, hit the like button and check out the recommended video on your screen.